Hi guys, welcome to our fourth video in chapter 11. This video is all about empirical and molecular formulas. To begin our discussion of empirical formulas, we have to start with what's called percent composition. This is something that any analytical chemist is going to be responsible for in order to determine the identity of an element, okay, or a compound. Ultimately, we're going to use this to find molecular formulas. So percent composition is defined here as the percent by mass of each element in a compound. So in a very simple example, if we take a 100-gram sample and it has 55 grams of element X and 45 grams of element Y, then I can do some percent calculations in a very straightforward manner. Take your mass of the element, divide it by the mass of the compound, multiply by 100, and that gets you your percent by mass. In our example, take our 55 grams of element X, divide by 100 grams total, by 100, and we get 55% element X. Same calculations get us 45% element Y. So as long as you're comfortable with percent calculations, these should not be that difficult. On the other, or say like on a complicating factor, perhaps we are instead given the chemical formula and asked to predict the percent composition. In this case, the thing you want to remember to do is divide the mass of the element by the mass of the compound. And I think it's actually fairly straightforward. So I'll show you an example with water to begin. So we'll do hydrogen first, and then we'll do oxygen. And the key for this is remember that your total mass is just going to be the mass of your entire molecule, right? So we'll do the percent hydrogen. We're going to take the total mass of our hydrogens in here. And so we have two hydrogen atoms, right? H2O, there's two hydrogens. And each one would have a molar mass of 1.08 grams per mole. And we're going to divide that by our total mass of our compound, which you should be able to calculate on your own for H2O as 18.02 grams per mole. Now I can see very importantly that my units will cancel out, which is necessary for a percent calculation. I'm going to then multiply this by 100, right? Because it's percent. And if I do my math correctly, I'll get 11.2% hydrogen as my answer. So I'll say, cool, that's 11.2. And we could do the same thing for oxygen if we wanted. We could also just say, oh, if the rest is oxygen, we can just subtract 11.2 from 100, and that'll get us our answer. But I'll show you the long way just because for completeness. So we take our 16.00, that's the molar mass of oxygen. We only have one of them, so we don't need to multiply by anything. So one oxygen, and then our total mass of 18.02 grams per mole here. Units cancel again, absolutely correct, times 100, and we're gonna get 88.8% by mass oxygen, right? So there we go. There's our 2% by masses for each compound in water. Now, this is all great. However, it's going to produce what is called the empirical formula. This is defined as a compound, the empirical formula for a compound is the formula with the smallest number of mole ratios of elements. So when we first do these calculations, we're going to get something very similar to an ionic formula, which has that lowest ratio of elements in your ionic compound. Likewise, an empirical formula is your lowest ratio of elements in a compound. This is, of course, not something we can give as a molecular formula. Remember, we talked about how molecules are not able to be, their chemical formulas are not able to be reduced because they're actually forming molecules, like physically discrete entities. So let's look at first how we would calculate an empirical formula from some percent data, and then we'll look at how we can use that empirical formula to calculate a molecular formula. So with my empirical formula, I've got this example, and I think it'll be best to just walk through this example with you guys and show you exactly how this is done. And so here's our example. It says, determine the empirical formula, which I've highlighted in red. That's what the question's asking us for, of methyl acetate, which has the following chemical analysis: 48.64% carbon, 8.16% hydrogen, and 43.20% oxygen. And you might look at this and be like, wow, Mr. Hitt, there's no way to go from moles or from percent to moles. And I would say you are maybe correct in an abstract term, but I want to direct your attention back up here. I didn't just choose a 100-gram sample just for fun. I chose a 100-gram sample because it made our percent calculations very easy. So let's go back to our example and let's make a valid assumption. Let's assume 100-gram total sample. Then when we have this 100-gram total sample, we can assume, or we not can assume, but if there's 100 grams in total, if 48.64% of that was carbon, I can also say that I have 48.64 grams of carbon. Since my total sample was 100 grams, if 48% of that is carbon, that means I'll have 48 grams of carbon. So that's why I'm going to assume I have 100 grams in total. And now that I have grams, I can multiply this by 1 mole over my 12.01 grams. Grams will cancel, and I will calculate that I have 4.050 mole carbon. And I'm going to do the same analysis for my hydrogen and my oxygen. Hydrogen is now 8.16 grams of hydrogen times my 1 mole over my 1.008 grams. And I get 8.1010 mole of hydrogen because my grams, of course, cancel out. Last one, we'll do our oxygen. Oxygen has a mass in this of 43.20 grams, of oxygen times my 1 mole over 16.00 grams, and I get 2.700 mole of oxygen. Okay, so I have calculated that in 100 grams, I'll have this many moles of carbon, hydrogen, and oxygen. Now, you guys know from, of course, the definition of an empirical ratio or an empirical formula, we're dealing with the smallest number of mole ratios. And so just like in a chemical formula, what it's really giving you is that I'm going to highlight that in red, I guess. Highlight it on red. Cool. But just like in a chemical formula, H2O for water is telling you that you have a ratio of 2 oxygens for every 1, or I'm sorry, 2 hydrogens for every 1 oxygen. We're going to set these in a ratio in order to determine how many of each element we have in our molecule, like in each individual molecule. So I'm going to take the smallest number here. So I'm going to start with my 2.70 moles of oxygen, and I'm going to divide all of the numbers by that smallest mole count here, and we'll see where that gets me. Okay, so I'm going to begin with my carbon. So I'll take my 4.050 mole of carbon, and I'm going to divide that by my 2.700 moles this time. I'll divide that, so I'll leave this unitless for now. But if we do this math out, and I encourage you to do this yourself, you're going to get 1.50 mole of carbon. I'll do the same thing for my hydrogen. I'm going to take my 8.10 mole of H, divide it by that smallest number, divide it by the 2.700, and I'm going to get 3.00 mole of H. And then finally, I'm going to do my oxygen. So 2.700 divided by 2.700 mole of oxygen divided by 2.700. And you get 1.00 mole of oxygen. So we're close. These are starting to look pretty good, right? They're not crazy numbers anymore. We've got very almost all integers, right? Our only problem is that this mole of carbon is still a 1.5. Now, my mission is to get this all set into individual integers, right? When you have a chemical formula, it has to be integers. So if I consider, what if I multiplied if I consider how to get this 1.5 into a whole number ratio, well, if I multiply it by 2, I'll get 3.00 mole of carbon, which is an integer. Well, if I multiply my carbon by 2, I'm going to multiply every other element by 2, right? What I do to one, I got to do to the others. So that would give me 6 moles of hydrogen and 2 moles of oxygen. So here we are. We have calculated from some percent composition some whole number ratios of elements. And this gives us the chemical formula. If I write this out, you've got C3, H6, O2. And that can be that is our empirical formula. That is the empirical formula of our acetate. So, I'm sorry, not our acetate, our methyl acetate, right? Yeah, methyl acetate. So there we go. Our empirical formula, C3H6O2. Awesome. So this is all good. We've calculated our empirical formula, or recall that is our most reduced chemical formula. Okay, so I've got just a little bit left in this video. So I'm going to push just a little bit, hopefully past our 10-minute mark. And so let's talk molecular formula, right? This is the actual specific number of atoms in one molecule of a substance. So this is the one, like the holy grail of chemical formulas. And this little second bullet shows us the fairly straightforward method of getting the empirical formula getting the molecular formula from an empirical formula. All you have to do so first of all, we have to determine the molar mass through experimentation. So you'll be given the molar mass of the actual compound, and we compare that molar mass to our mass represented by the empirical formula. So in this example here, if we have an example of acetylene, the molar mass of acetylene is 26.04 grams per mole, where the mass of the empirical formula was 13.02 grams per mole. So if you do this out, you divide your experimentally determined molar mass by the empirical formula, you're going to get 26.04 divided by 13.02, which would get you 2.00. And this would indicate that you have 2 of your empirical formula units in each molecule. So you just multiply your chemical formula by 2. And we'll see some examples of how to do this in class. But down here, I have just quickly summarized. I snipped this out of the textbook. Here's our flow chart for how we can determine the molecular and empirical formulas from percent composition or mass data, right? Again, we'll get some practice with this in class. So I would say have some passing familiarity with this and just make sure you're ready to go when you come to class. All right, guys, that's all for this video. Thank you for listening, and I'll see you in the next one.